Now here's the theorem again, but you can see this if highlighted here. If there's this arbitrary second order operator, and if we can factor, and using that idea of the first order equation, integrating factor, we can show its uniqueness and existence. And the algorithm is pretty practical, so you can actually calculate this one, and you have a shape of the answer. And of course, next part of the question, if I have second order arbitrary linear operator like that, can I factor it? And the answer is yes, and it's quite amusing. First, look at this fact, and this is what's happening. If you can factor this one, it actually unfolds it in this way. So we're going to set this one into whatever the given coefficient A, that to be B, and solve for P and Q. So that part is actually fairly simple. If you start with d squared axd plus bxi, this is the second order operator associated with the second order linear second order equation, then if it can be factored, can we describe this P and Q? It is really neat and simple. The Q, the answer to this Q, the solution to this nonlinear first order equation, b minus ay plus y squared, and P is simply a minus qx. So if you take that and actually put it in here and unfold it and use this property, you can easily show this recovers ax and bx. Let us first explain the motivation, and if we have to solve this problem, and this is how you can approach, and then we'll give you a straightforward proof. Of course, the given a and b, these are the coefficient functions, then you're going to set this q prime pq, that's this part here, b, and p plus q a, and that's how this one unfolds. If you can find p and q like that, and of course you can show easily, because of the lemma, we can show these two things are exactly equal to each other. So let's solve this differential equation for p and q. It's a system of equation, but if you look at it, it's not that bad. There's not even a derivative for p here, and p is the only part. So if you just simply substitute p with a minus q into that equation, then you end up at this equation, which seems like first order differential equation, but it picks up q squared, so it's not linear anymore. But here, if you isolate and make it into standard form, is a q prime and bx and ax. These are functions, and x and q squared. This is typical standard form nonlinear equation. And you can find my a series of a long video about this first order existence and uniqueness of first order nonlinear equation. So we know it exists if you give some conditions. So we know it's a one-dimensional vector space. It's not a vector space, it's one-dimensional objects. That's how we kind of enumerate the solution space. Well, that explanation is almost a proof, but this is how mathematicians usually prove, state the proof, not stating that how we discover this qx. We just simply set out what qx is. We're going to set the qx be the solution to this differential equation. If you look at our discussion earlier, it doesn't have to be any particular solution. Anything that's satisfying this one will work. So using a as part of our domain and putting down some initial condition will give you specific functions. So when you prove something specific, it's better than just saying any choice. So I will make the specific choice, ya being 0, and that will be function, one and only one function that satisfies this initial condition. That's our qx. And this condition is not important at all. And px is ax minus qx, right? So this is the setup when all we have to show is that this q and p satisfy the assertion, which is showing this two first order operator multiplied and becomes d squared ax d plus bx. So use a lemma to expand this. The lemma says that d squared and simply the sum of the coefficients of I, I'm missing I here, and multiplying p and q here, but you have to add the derivative of the coefficient of I part in the second vector there. But q was solution to this equation, so this q prime plus pq, well, p is a minus q, so if you substitute it back in there, and what you get is q prime, that is b minus a q I'm missing, sorry about that, plus q squared because of this differential equation that q satisfies, and pq is p is a minus q, so is a minus q, so this thing and that thing is supposed to cancel. Sorry about that again, there should be a q in there. Then it just gives you b, and that's a proof. So let me summarize it here. Earlier we showed that if this second order linear operator factors, then you can use that the decomposition of this linear second order operator to show it existence and uniqueness. So if we can establish that everything that we consider in degree 2 factors like this, then it completes the existence and uniqueness of all second order linear differential equations. Here we're asserting that yes, it factors all the time.